Okay, so welcome back everyone to our continuation of the discussion of row updates in relational database systems. All right, and it's that time again. It's the change from the disk-based PostgreSQL to the main memory-based MonetDB system. Let's see how MonetDB implements row updates. Okay. Of course, MonetDB will be subject to the same probe queries, to the insert query. So we will insert particular new values into the ternary 3-column table. We will update a particular row identified by a predicate, or maybe a set of rows identified by predicate, and then set column C to a new value, or we will delete given rows or those that satisfy this particular predicate. These are the probe queries. Now, MonetDB is a column-based database system. So, for example, for the update case, so for this case, we expect that only the column but C, only the but for column C is indeed affected. So the A and B columns held in different buts should be unaffected by this particular update. And we will see how MonetDB implements that. It's different for the insert and for the delete case, where entire rows are either being inserted or entire rows are either being removed from the table state. In this case, we should expect all column buts to be affected by this. And we will see that in a very obvious fashion in the insert case and in a more subtle fashion in the delete case. All right. And all of the subtlety and the interestingness derives from the fact that MonetDB tries to achieve the same thing as PostgreSQL. Particular updates, modifications to tables should be visible only to that particular user or application and not system-wide, at least not until the user or the system decides that system-wide or global visibility of the updates is called for. Until then, such updates are supposed to be locally visible only to the update performing user. Okay, so to save the system from maintaining multiple copies of multiple but copies to provide one particular user a view on her table and all other users the global view of the table, to save the system from maintaining such multiple very memory resource intensive copies of the column buts, MonetDB implements so-called delta table logic, so delta tables, all right. And delta tables are a place where the system maintains a protocol of what has actually been changed in the buts. So what deletions have been performed, what updates have been performed. This is not immediately applied to the buts, that would mean immediate global visibility, and that's not what we want. But each user has its own copy of delta tables where updates and deletions and so on are being recorded. And these updates, these recorded updates in the delta tables are being used to provide the local update performing user with her view, with her updated view on the original table. So the update performing user will see a state of the table that is impacted by the delta tables. All other users, the global visibility of the same table, will not take into account these data tables and will see the unaffected, non-updated version of the table as is required. At one particular point, the contents of the data tables, the recorded updates, will be applied to the actual column buts themselves, and from that point on, all the updates will be visibility to everyone globally in the system. Okay, so delta tables. How are these being maintained and what role are they playing in updates in MonetDB? Let's see. So let's first look at the delete case. So given table ternary as we know it, delete entire rows or one entire row from it. This would be SQL DML statement that we are issuing, and we're identifying one particular row in the ternary table, the row with A value 981, and we know there's only one such row because the column A is indeed a key column. So if we specify explain here and have MonetDB list the mul program that corresponds to this updating query, then this is an excerpt, the crucial parts of the mul program that we would see. We would access the visibility, the current visibility information for the ternary table. And as you can imagine, this visibility information is something that can change when we perform, for example, deletions. All right, so we would access the current visibility information, and we would access the current state of the A column but. Okay, because this is the column that we need to read because we have to evaluate this filter predicate here. Okay, the implementation of the logic of this filter predicate is happening in this particular row. So let me highlight that. So I'm talking about this row, the algebra theta select row now. All right, so what's happening here is that this visibility information, the ternary visibility information, is being applied to the A column but. Okay, so only the now visible rows in the A column but will be will remain. All right, and then we will evaluate a predicate. We will evaluate a predicate on the remaining A rows, the remaining A rows in the A but, and this is the predicate. We would check whether the tail value in these rows equals to 981. So this is a very simple way to specify and represent a predicate in mul, because as you know, each but only has a head and a tail column. Such predicates are only ever applied to the tail columns, so there is no need to specify which attribute or whatever is being affected by this predicate. It's a given that we are selecting on the basis of the tail column, all right? And we are requesting that that we find the rows in which tail column equals the value 981, all right? So these are the rows that are going to be deleted. These are the rows that are going to be deleted, and this is thus a very appropriate name for this mul variable. These will be the rows that are going to be deleted. But the deletion is not being performed on the A, B, and C column buts yet. It's not performed there yet. But what we do is we create a record. We write a protocol about which rows are going to be deleted later on. Once the global visibility is being implemented and these rows really should be deleted, these are the rows identified by deleted rows that have to be removed from the table state. Okay, and as you can see, this deleted rows but actually is one argument to this SQL delete call. And the SQL delete call will exactly write this protocol for us. It will write a protocol saying that this particular table is affected by deletion. Some rows have to go from that table. These are the OIDs of the rows that need to go once we want to implement the effect of the update. We are not doing that yet, but we are writing a protocol about this. And everything I've just said is being reflected down here. So here you can see how the algebra theta select is actually performing its work. So it's a mixture of applying visibility information. So there's some implicit algebra projection going on and the evaluation of the predicate on the tail of the but. Okay, and here you can see how as SQL delete is supposed to not implement the actual deletion yet, but to write a protocol about what has to be deleted. And we already know one method, one measure in MonetDB where such deletions, how such deletions can be recorded. It's in the visibility information. The visibility information that we can request using the SQL TID function. We do this in all the queries that have been performed until now in MonetDB, and the SQL delete function will make sure that the deleted rows are being removed from the visibility information or that we can access here using the SQL TID function. This is how the current deletion is being implemented internally. Only the visibility information is being affected, not the actual column butts A, B, C themselves. Okay, so that's about delete. How about insert? Insert is not that spectacular, so that would be the insert DML statement that we are performing. So we specify 3 new column values for the A, B, and C columns. You see that the types match. That's an integer, a text value, and a floating point value or a double value that fits the schema of table ternary. That's the insert we are going to perform. If we perform the explain here, we will see a long mul program. The focus, the core of that mul program is shown in an excerpt here. And as we've already foreseen, such an update will affect all 3 columns, the A, B, and C columns. All of them receive new values. Okay, so we are writing a record. We are writing a record, a protocol about the fact that the A, B, and C columns are affected and will receive new values. You see the 3 new values here, and you see that the A, B, and C columns are being passed to the SQL append function. The SQL append function is exactly the function that will write the protocol. In this case, it will write the protocol to the delta I, the delta insertion table. Let's call it like this. It's the delta insertion table that will hold the protocol of all the rows that have to be inserted into a particular column butt. All right, so what we do is we write the protocol, but we do not change the A, B, and C column butts of table ternary themselves yet. Okay, so again, the effect on the actual column butts is postponed, just like in the delete case, where only the visibility information was being maintained. So that would be the insert case. So how about the update case? In the update case, we will identify a particular row, okay, or a particular set of rows, and then modify given column values. In this case, only the C column is affected. So how would that go? This again is the explain output, the excerpt of the mul program that we are seeing in the terminal, and we'll do that later on. So it starts out as usual. So we will access the visibility information. Okay, we will access the A column butt because we have to prepare for the evaluation of this filter predicate. Again, the filter predicate is evaluated using the theta select function. Okay, so what we find here in the updated rows but is all the rows, maybe it's only one row, maybe none, but it's all the rows that are being affected by this particular update. Okay, so we use this is a collection of OIDs, all the affected rows. We use this information in the next algebra projection call. So we use the algebra projection call passing the updated rows but here, and what we will receive is the A values that are going to be updated. So we use this updated rows information, the affected rows, apply it to the A column butt. All right, and what we will see is the affected A values here. Actually, it's not quite strictly needed in this particular version of the mul program, but this is how MonetDB currently compiles such an update. All right, so this would be the affected A values, and we would replace the affected A values by -1s here. Okay, so all the currently stored A values, they would be replaced by -1. You see that is an algebra project operation. We haven't seen that before, but you can probably guess what it's doing. It's taking this particular butt and all the tail values are being set to -1s. So what we have here with the updated CBUT is all the affected rows in the head column, the OIDs of the affected rows in the head column, and in the tail column, -1s. This is exactly the payload of this update. These are the affected rows. The new C value in this row will be -1. Okay, and again, this update is not being performed on the actual C column but we are writing a record in the delta U, in the delta update table for now. All right, and this is what the SQL update function will do for us. It will write a protocol about the fact that the ternary C column has to be updated. All right, these are the affected rows. These are the affected rows. And these are the new C values that are going to be placed in these rows. All right. Again, SQL update writes a protocol, but does not change the C column but yet, because other users, other applications, should still not see our updates. They should see the old state, the global state of the ternary table and its C column, for example, and we make sure that this delta U table and its effect on the ternary table remains user local. Nobody can see what we have been doing here. So now we have written protocols. We have written protocols in the visibility information. This has been affected by the delete. We have updated changes or recorded changes and written protocols in the delta I, the insert, and the delta U, the update table. Okay. When the time comes and the local user wants to see the current state of table ternary, then it's the time where we use this recorded protocol information and indeed apply it to the ternary table and its buts to really construct the updated, deleted, inserted state of the column buts. And this is what would be happening here. So we would look at the original but for column C, for example. That would be the globally visible but for column C. Everybody can see this version of the but, and everybody would see the non-updated versions of the rows in this column. Let's say there are only 4 rows in the C column and they have the values V0 to V3. Okay, and now let's suppose that one user has performed a number of updates on this. He has updated V2 into V2 prime. Okay, he has inserted a new value V4. Okay, and value V1 should be gone, so it should be affected by a deletion. All of these SQL DML update operations would have been recorded in either the visibility table or the delta tables. And this is the contents of the data tables that reflect the update that I've just mentioned. For example, the update of the V2 value, this is held in the row with OID 2 at 0, okay, is reflected by these 2 rows in the delta U tables here. Okay, so that these 2 rows belong together is reflected by the fact that they carry the same OID here. That 2 at 0 identifies the affected row. The V2 prime would be the new value to be placed in the affected row. Okay, so that would be the implementation, the protocol of the update. The protocol of the insert is just this. It's the new value V4 that will be assigned a new OID value that we could then use and just append or add to this original column. And the visibility information would reflect that the row with tail value V1, which has OID 1 at 0, has to be removed. And this is exactly what we see in the visibility information here. So in the visibility information, you see that here in the tail column, the 1 at 0 OID is missing. If we apply this visibility information using algebra projection, the the row carrying the value v1 would be removed. So a cascade of operations applied to the original column but table using this replacement information, then adding stuff, to be inserted stuff, and then applying the visibility restriction will lead to a view of the column table C that represents the column C after these three updates. We will see the column C as the modifying user. We will see the column C after it has gone through these modifications and the applications of the updating information. All other users, the global users, will just see this version of the table. All right, and it's way cheaper normally to maintain this very limited, very small protocol of updates here and the visibility information than to maintain extra copies for each modifying user of all the column parts here. Recall that this might be, in a real system, this might be a multi-million row table. And maintaining copies of these is certainly more expensive than maintaining just a few updates that might have been performed in the last time frame. So this is what we are going to see if we look at mul programs that try to reconstruct the updated view of the column C, for example. And we will see this in the interactive terminal in the next video. So what we would do is we would load the yet unmodified globally visible column but for C. We would then apply the delta U, the update information, the protocol, and there is a particular function to do that. It's the but replace function, and the but replace function would read this delta U, this update protocol information, and apply it to the original column C but. Once we've done that, we would use the but append function in mul to read the delta insert table, the delta I table, and append new information onto the column C but, okay, or view of the column C but. And as a last step, we would apply, as we know, algebra projection to implement row visibility to enforce the non-visibility of rows that should have been deleted. Okay. So as a local user, whenever we want to view the content of column C, this is a stack of operations that has to be performed to give us a view, the current view of the updated C table. Everybody else would just see the original C column but. Only when we decide to really make these changes globally visible. Okay, so these are changes that everybody should see affected. We will perform a particular command in MonetDB, the so-called commit command, which says I'm content with all of these changes. These are this is a new state, this defines a new state of column C that should be globally visible. I'm committing to these changes, and transaction management, the commit processing inside MonetDB will then make sure that all users will see a new column but that reflects all the protocol updates and the visibility information. It's time to really modify the column buts for column C, for example, but only then. Okay, so this has been a dry run. So lots of slides, lots of talking. In the next video, I will show you really how this is being performed in MonetDB SQL and the MonetDB mul side of things. So we will just replay what we've just seen here in the next video. And I can only recommend that you stop this video now. It's over anyway. And continue with the next video. These are really sister or twin videos in which the second part will really inside the MonetDB client perform all the stuff that we've just seen here. And I think there's more stuff to be learned. Okay, so stay tuned for that. See you then. Bye.